Okay, so in this video, we're going to go over more detail about internal validity. Specifically, I wanted to mention that in terms of main challenges to internal validity are listed on this slide. Here you could see Drake and how he feels about internal validity. You want to have a good internal validity. We have 6 main points to be aware of. You want to make sure you don't have a biased researcher. Make sure that, this is an alternate explanation to your finding, right? Maybe you didn't find that fat increases intelligence. Maybe you found that it's not that. It's just that you have a biased researcher. Maybe that's just the case. In addition, you might have a researcher that's aware of the hypothesis. And then we're actually going to go into design confounds in the next slide, but you want to make sure you avoid self-selection because people might select into different conditions, and that might help explain your finding. And you have to make sure you don't have a third variable problem, meaning you have some other explanation, some other variable that's influencing the outcome. So for example, it's not fat that's leading the mice to do better. It's that they were already smarter to begin with, right? And you want to make sure that the explanation is not due to poor measurement. And by explanation, I meant like the finding, right? You want to make sure that you didn't get a finding just because you as a researcher or somebody you trained wasn't as good at measuring one group versus the other, and you found a difference not because there is a difference, but because you measured poorly, right? You measure your DV poorly. So for example, if you're counting signs of aggression in children, maybe you were more lenient for several of these reasons, right? Poor measurement, bias, you knew the hypothesis. And then in addition, you want to make sure there's no environmental confound, right? Were people more tired in one condition versus the other? Were people more aware? Did people have a different experience across the experiment because of some environmental factor like lighting, temperature in the room, time of day? So given that we've reviewed those, let's move on to, we're going to move on to types of confounds, focusing on design confounds and in selection effects. But you know what? Let me go back because I think it's good to go over this example. We're going to have examples like this on the exam, and I want to make sure you're able to answer examples like this. So in this example, let me read it to you. So a recent headline read, "School lunches make kids fat." Right? So that's a causal claim. School lunches make kids fat. The article cited a study comparing children at 2 schools. The school with lower obesity rates had fewer children who ate school lunches. Right? That's where they're drawing this conclusion. The other school had a greater percentage of obese children, and most of these children ate school lunches. All right, so based on this, children who eat school lunches at one school had higher rates of obesity than another school where most kids did not eat school lunches, right? So this is what they're using to make this claim. I have more information below that kind of helps clarify it, but even with that level of information, I'm hoping that you could figure out, well, can they make a causal claim just based on that information? But I give you more. So here I mentioned that no mention was made that many of the children who ate school lunches were also low income, right? That's key. They were also low income. This may be, and then here I just give it to you. This may be a third variable that is influencing the measured variable. Then I ask you in this question, what validity is being threatened by the potential confound of poverty or income, right? So I actually have the answer right on top, right there. I don't know where you're seeing it. It's probably over there, But you see the title of the slide, internal validity. That's the type of validity that's called into question. So you might get a question like this. But now, given that you know what kind of validity is being called into question, think about, do you know why? Like, why is it that internal validity is an issue in this experiment? Well, let me point you to two things. One issue, there's no signs of a manipulated variable, meaning they did not randomly assign children to their IV, to eating school lunches or to not eating school lunches, right? That's their IV. They're claiming that eating a school lunch causes obesity. So from that framing, that sentence structure, the way it's stated, you should be able to tell, okay, that's the IV. They're claiming this leads to that. And then look at the IV. Did they manipulate the variable? Did they randomly assign who gets school lunches and who doesn't? In this case, they didn't. They just found kids who were already eating school lunches and compared them to kids who were not eating school lunches. That's one issue. Issue two with making a causal claim. Well, it turns out that most of the kids, and I give you this information, most of the kids who eat school lunches are also low income. Now, might this help explain the obesity rate among this group of children, right? Being low income. Well, for example, low income children may have less access to healthier food. Low income children might be part of households where both parents are working, maybe working multiple jobs. Maybe they're not home to cook a healthy meal. So the children have to eat maruchan, eat like these, a cup of noodles, less healthy fast food. And that might explain why the obesity rates are higher among those children, right? So whenever you have an alternate explanation, a possible alternate explanation, you have an issue with the internal validity. Whenever you see that they didn't randomly assign the IV and they're claiming a causal claim, then you also have an issue with internal validity, right? So hopefully you see those issues in this study design, but then also keep in mind, can they claim temporal precedence? Which caused which? Well, is it that eating the school lunches leads to obesity, or children who are more overweight, do they tend to just eat more school lunches or eat school lunch more often? Now, that kind of seems like a weird direction for the relationship to take, right? But that's a possibility. You don't know that. You can't rule that option out. You have another issue with making that causal claim. So let's go a bit into specific types of challenges, confounds to internal validity, specifically design confounds and selection effects. So a design confound is an issue with a method that throws into question your internal validity. So here I have written down due to poor experimental design. So for example, if I made this claim that, so let's look actually at that second example. I make a claim about stereotype threat. I have the same researcher run everybody in the stereotype threat condition. And I have the same researcher, but a different researcher, run everybody in the control condition. But let's say, that's why I have these mean and happy faces, and they're kids, they're just cute. You have a researcher who just has a mean face. They just look angry, they're not angry, they just look that way. And they're running everybody in the stereotype threat condition. Then you have just a very happy, very positive, very welcoming researcher running everybody in the control group. Now I find that everybody in the stereotype threat group that had the mean-looking researcher scored lower, and everybody in the control group with a positive, happy-go-lucky researcher that in the control group, they did better. Who's to say that the researcher affect or the emotion they were displaying didn't impact their test score, right? Maybe it wasn't stereotype threat. Maybe it was some issue with my design. Maybe it was that mean researcher made people nervous, right? So whenever you have an issue with the design and the method, that might call into question your internal validity or the claim you're causing that, in this case, a stereotype threat influences ability, then you have an issue with the internal validity. Now, just to be clear, this is hypothetical. They take this into account, but stereotype threat has been shown across dozens or even hundreds of experiments to impact ability. So that's not anything we're questioning. But if you had this experiment and you had this issue with the researchers, then somebody might ask you, well, I actually saw how you ran the study. They would have to know this. So it probably might be somebody in the research team. Do you think that maybe that Omar influenced the outcome somehow because he's always has that resting professor face? So that would be an issue, right? So that is an example of systematic variability. A systematic issue, meaning that everybody in one condition received the mean researcher or mean looking researcher, but maybe they're actually very nice. And everybody in the other condition received a different type of researcher that might have influenced the outcome. So that's what systematic means. Everybody in one condition gets one completely different experience than everybody in the other condition, and it has nothing to do with your IV. Because we want the IV to vary, right? We want people to get caffeine or not caffeine, or stereotype threat and not stereotype threat, right? The control group. But we don't want we don't want people in the stereotype threat condition to always get a researcher who looks angry versus the control group, right? So here's an example that uses caffeine, my favorite thing in this world, maybe. Okay, my daughter wins, but caffeine, I love it. And we have decaf. And we're interested in seeing how caffeine and decaf are related. Well, specifically, we care about caffeine, not so much decaf. We care about seeing how caffeine might be related or might cause increase in attention, right? Now, we have this experiment, but then for some reason, I end up with a design where I have everybody in the caffeine situation participating in my study at 8 a.m. and everybody in my decaf situation participating at noon. Let's say I find no findings. I found no difference. That's great. I wasted my time. But is there some challenge to the internal validity in this experiment? There is. Spoiler alert. Wait, can't say it afterwards. But there is a challenge to the internal validity because in one condition, caffeine, everybody participated at 8 a.m. Now think about how that time of day may impact people. I'm looking at attention. I'm working with university students. University students tend not to like 8 a.m. classes. I remember being a university student, I would wake up at 10 a.m. was early for me to be in a class. So take that into perspective. And I'm getting students, and my findings, or let me restate that. I'm finding that students in the caffeine condition are actually doing worse in attention compared to the decaf situation. So maybe I'll claim the inverse effect. Well, it turns out that caffeine makes people sleepier. It negatively impacts attention, even though it might give them energy, right? Now, because of the systematic issue where everybody in the caffeine condition participated at 8 a.m. and everybody in the decaf situation participated at 12 p.m., I have this third variable issue of time. Time, not caffeine and decaf, might explain what's actually going on. Maybe it's not the caffeine, maybe time of day impacts attention. People at 8 a.m. are going to have a hard time, especially students, are going to have a hard time paying attention than students who observe a lecture at 12 p.m. So if you felt time of day was a confound, one thing you could do is just randomly assign people to the different times. So if the only time you can run participants was 8 a.m. and noon, that's not necessarily an issue. But if you made sure that people, well, first of all, you have to randomly assign people to caffeine or decaf to make a causal claim. So remember, you do have to have random assignment. So you assign people to caffeine, assign people to decaf. But then within caffeine and within decaf, if you were worried about time of day, you would randomly assign people to the different times of day. So you would get about an equal amount of people in the caffeine condition getting 8 a.m. and noon, and you would randomize this process, and same thing for decaf. Now we're not worried that time is impacting the differences. If we see a difference after doing this, we're on the stronger ground to make the claim that it's caffeine that helped improve attention, or if we found the opposite, it's caffeine that hurts attention. Or another solution is to have everybody go at the same time. So when you control for variables, usually people use it in this sense that, okay, fine, then make sure everybody gets the same experience. I've factored out time as an explanation for my outcome. You can't say that time is what influences differences between these groups if everybody participated at the same time of day, right? So I've factored that out. I've controlled this variable. That's what it means. When I control this variable, I've held it constant. I've held it the same for every person. Everybody gets 8 a.m. So let me actually review that really quickly. When I hold something constant, it's the same thing. I'm holding it the same for everyone. Now, other things you could do to address design confound, or other situations where you might have design confounds, are addressed here. I kind of addressed it in the previous slides, but if you have time, you could have people go in at the same time at 8 a.m. You could randomize people to the different conditions if you're worried, or not different conditions, but different times of day, right? This other third variable, that's not your IV. You're worried it might also impact your DV. Well, okay, then just randomize people into the different times of day. That way you don't have to worry about it. I think the easiest way is just to hold it constant, right? To give everybody 8 a.m. or everybody at noon. And it doesn't have to be that exact, right? If you're going to say morning, well, okay, you get some people between 8 a.m. and 9 a.m. And then consider this. Consider if you were doing a study, just to kind of give you an idea of how might this impact you, how this impacts people. Let's say you had all women participate at 8 a.m. on a math ability score. You were comparing male to female participants. And all the female participants participated at 8 a.m. because you had a female researcher who's available at that time. You wanted to match the researcher to the participant by their gender because you were worried about stereotype threat. And it just happened to be that this female researcher is only available at 8 a.m. and your male researcher is only available at 2 p.m. Okay. Think about that situation. Have all the women go at 8 a.m. and then you find that the women do worse than the men. Okay, some researchers might claim, well, see, like it looks like women are not as good as math even today compared to men. But somebody who's part of the team, hopefully, or at a conference, especially if you provide them with the data regarding when you recruited participants, might call that into question. Might say, wait, you had all the female participants participate at 8 a.m. How do you know that doesn't explain the difference? How do you know it's not that just the female students, because they're students and it's early for a student? How do you know that it's not that they were just very tired and had a hard time concentrating and doing well that early in the day? Right? So that's something that might impact, well, if this was published without somebody catching that, that might impact how people are trained, people's perception of women in math, people's views that things haven't improved. So that's why this would matter, right? So this is a little bit more difficult to explain. What is not a design confound? So if you were worried about time of day as a design confound, right? An environmental confound that might influence the results of your study. If time of day was random for both your caffeine and decaf group, you wouldn't worry. So if you had a situation like this, when it was non-systematic, just random, right? Some people got 8 a.m., some people got 10 a.m., some people got 3 p.m., but you had these random times across both caffeine and the decaf situation, you wouldn't worry. You would worry if you had this, if it was systematic, meaning people in one level of the IV, so caffeine, always got one experience. They always got 8 a.m., they always got the hot room, they always got the mean-looking researcher. That's what it means for it to be systematic, right? That the people in one group consistently got a different experience from the other group. Okay, now let me go back. So keep that in mind. If you have unsystematic variability, meaning random random variability based on this third variable you're worried about, or the researcher's worried about, you don't have to worry. You have to worry about it when it's systematic. Just to give you an example, this is what it might look like, right? Let's say you collected the data. You weren't able to randomly assign participants to time, but then somebody brought it up, well, what about time? Do you think time of day might impact the differences you're observing? You went back to the data and you saw in the caffeine group, you had some people go at 9 a.m., some people at 3:15, some people at 12, some people in the decaf group, various random different times. Good, you're good, right? It's random times. It's not systematic. You don't have to worry about it. Now, moving on to selection effects. It's different from what we just reviewed. So it's not so much the design of the study. Well, actually, it kind of is part of it. Because in this type of threat to internal validity, the issue is that your design lets a participant choose which condition to go into, right? And we've kind of reviewed previously what that might lead to, but I'll review that here. But the main issue is that by letting people self-select into conditions, you might get a qualitatively different group in each comparison group. So what I mean is, if you let people choose a caffeine versus decaf, you might get people who drink caffeine more often in the caffeine group. You might get people who are more resilient to caffeine in the caffeine group. You might get people who I don't know, who are sleepier in the caffeine group, right? Now let me give you another example of why self-selection is an issue in a study design. Let's say I had a study where I recruited 5 to 10-year-olds and I let children choose if they wanted to do outdoor play or sit on a couch and use an iPad. Okay. And let's say I had this age range that was from 5 to 10 years of age. Let's say we go a little bit older, up to 13. And I find that, okay, so we let them do that. Then I give them some cognitive test. Well, it looks like children who use the iPad are actually smarter. Maybe there's some benefit to learning on an iPad versus playing outside. Now let's say let's make it more comparable. So instead of just playing outside versus being on an iPad, let's say the participants had a choice of doing a math activity by hand or do a math activity on the iPad. Now the math activity by hand was fun, used blocks, was interactive. Same thing for the iPad one, right? It was a fun iPad activity, and we let participants self-select. Now one situation that might come from this is that the older kids might more frequently choose the iPad. And really, it's not the iPad that's leading to differences in cognitive ability. It's that we're getting the older kids who have, just in terms of their cognitive development, are more advanced. So it's not the iPad that's causing this increase in intelligence. It's that the kids who self-selected into the iPad condition are in general older than the kids who self-selected into the block activity, where you might have younger kids. Now, when I came up with this example, it was less common for kids to have iPads, right? People were kind of torn on that. People are kind of still torn on that, but it's kind of more acceptable, I think, now for younger kids to use an iPad. But just the point is that because you're letting participants choose which condition they go into, you lead to groups that are already different, and that difference impacts your DV. I'll give you a more concrete example. So here you have a study where you're comparing two groups, and they only experience one condition, right? And this condition, one second. You have two conditions. You have a very rigorous training. You're trying to get them to improve on exams. It requires 8 hours a day of training, of work for a week. Whereas one group just has to do something lighter, 1 day of training versus every day. Or maybe they just take one class, right? I pay them the same amount because just based on the IRB, I'm supposed to compensate people equally, but I let them choose. Now, yes, this is meant to help people and improve their study skills, but just imagine who would choose a more rigorous training versus who would choose the day training. Now, some people might argue, well, maybe people who choose the week-long training are more dedicated. Fine, let's go with that. So if you get people who are more dedicated in the more rigorous training, maybe they've already done a bunch of studying. Maybe they've already practiced studying in the past. Maybe they have more familiarity with different studying approaches, and you're getting those type of people in this more rigorous experience, and you're getting people who want to get this over with in the day experience, right? So they're already different to begin with, and you get this group who gets a more rigorous training, and they do better in your exam. right? The exam you give them, or your test, or your measure of studying ability, whatever it is, they do better. And it's not so much that they've learned more, but maybe they did. But the thing is, this group was already more experienced, more motivated. So maybe that explains the difference more than your studying technique you developed for students. Here's another interpretation. Maybe students who took the week-long training, maybe they have more time. Maybe they're getting more financial aid. Maybe they're getting more money, more financial help from home. Maybe they have saved money. The point is, maybe they have more time to study. Maybe the students who take the day option only have that day, only work two jobs, commute from very far away. They don't have the time. They get very little sleep. They don't have time to waste on a week-long training. So maybe this group did worse, not so much because this day training didn't work or because the other one was so much better, but because they're tired. They're not getting enough sleep, right? So there's these alternate reasons that might result if you let people self-select into the different conditions. So ideally, you want to avoid self-selection to avoid selection effects. Some things you can do. Well, first of all, one thing you can do is use random assignment. That means if you were a participant, I would not let you choose which condition you went into. I would randomly assign you to the day training versus the long training, right? That's the most straightforward solution. I can also use a matched group design, right? So if I thought there was some quality about participants, right, that led to there being differences or that created an alternate explanation to the findings I'm observing, right? Then I might match people based on this third variable. So here you have a diagram from your textbook, and here you have two groups, right? These two groups represent two different groups of participants. So you've already assigned people to group 1 and group 2, right? One or the other. Now let's say you were worried that, okay, well, what if people who have a higher IQ just perform better on this math test? Maybe it doesn't have to do with my IV, right? So actually, this is kind of confusing because group 1 would represent level 1 of your IV and group 2 would represent level 2 of your IV. So let's give them a new name. So let's say group 1 is caffeine, group 2 is decaf. For some reason, I think that caffeine impacts ability on some math test. Okay, but then I'm worried. Well, okay, what if IQ actually explains how well they do? Okay, well, how can you factor out IQ as an explanation? You can randomly assign. Don't let them self-select into caffeine or decaf. Or you can match them. You can match them based on IQ or based on this other variable you're worried about. So for example, going back to the group 1 and group 2 or caffeine and decaf, I measure their IQ and I match high IQ with high IQ people, and then I compare those people and see how they did on my test. Then I have people who are on the second level of IQ, so second place compared to the highest. So then I compare those people. And I keep going until I get to the kind of feels mean, but the lowest scores, right? I get to the lowest IQ scores and then I compare them, and then I see does caffeine result in the difference between those individuals on this exam I'm having them complete, right? So now intelligence doesn't provide some alternate explanation on how well people are doing on my exam. I'm only comparing people with similar intelligence levels, so we don't have to worry about that. So here's another example of what you might do. There was actually an experiment that was included in the previous edition, or the second edition of the Moreling textbook. And they looked at how plate size was not just correlated, but how the plate size I gave you, or the researcher gave participants, caused participants to get less or more food. So kind of as you would expect, people with a smaller plate actually ended up serving themselves less than people with a bigger plate. And they not only served themselves less, they ate less, right? So you might even get that, that advice every now and then, use a small plate. But let's say you were worried, well, okay, maybe, but how do I know that a person's weight doesn't have some influence on how much they're serving themselves? Well, if you were worried that this third variable might help explain what actually is causing how much food people are eating, then, well, you could match people based on weight, right? Now, if you carried out this experiment, yes, it kind of would be awkward, but that could be well, you don't have to make it awkward, right? People just weigh themselves on the scale, get their weight. You don't know they wouldn't know how you're grouping them, but you do have to reveal what you're studying at the end. But putting that aside, you would group people into the top 10% in terms of their weight, the top 20 to 30%, and you would keep going creating these groups until you get to the lowest 10%. And then you would compare these groups within these groups, right? So you would compare how much food people eat on the small plate versus the big plate, only comparing the top 10%. And then you would compare the top 20 to 30% and look at the difference between the small and big plates only for that group, right? So this is what you would do when you do a matched group design. All right. If you have questions, let me know. Reach out, email me, office hours. I'm here to help.